All right. Well, here, let's continue our discussion about the built-in voltage and how it depends on temperature in a diode. I'm going to go back to the notepad 1 second. Okay, so we were considering the work per electron required, the minimum work required to bring an electron around the circuit, to take an electron from the P side of the junction and deposit it into the N side of the diode. Okay? We said that at temperature 0, the work would just equal the change in the energy of the electron, which is just equal to the magnitude of the energy gap between valence and conduction band. So the work per electron would just be Eg. However, when we measured this in a real diode at finite temperature, we found that the work per electron required actually gets smaller as the temperature gets higher. It gets easier as we heat it up. And the reason for this is that at finite temperatures, we don't have to supply all the energy with the battery. Some of the energy can come in as heat from the environment, okay? Thermodynamics tells us that the change in energy per electron, in this case, should be equal to the work required per electron in this case should be equal to the change in energy, which is the energy gap, minus this term here, T delta S, which is the amount of heat per electron hole pair that comes in from the environment, okay? Oh, here's our drawing again. Get rid of this version. Okay. Well, the next thing to do is to put numbers into this, okay? So for this case, where we're essentially introducing two particles into ideal gases, we're introducing an electron into the ideal gas of electrons in the N-type semiconductor, and we're introducing a hole into the ideal gas on the P-type side of the semiconductor. The change in entropy can be calculated, and it's given by this expression, K Boltzmann times the natural log of the following. I'm going to write it out and then I'll explain the terms. Okay? So in this term, capital N sub C is called the effective number of states in the conduction band. Whereas NV is the effective number of states in the valence band. Here, N sub E, this is the density, it's the number of electrons. Well, it's the density of electrons in the N-type material. And NH is the density of holes. So these are numbers of electrons per unit volume in the denominator, and also number per unit volume in the numerator. So it's number of effective number of states per cubic meter. Now, if you haven't taken statistical mechanics, then I'm just pulling this formula out of a hat, and I'm not going to tell you where it comes from. But if you have taken statistical mechanics and you look at this for a little while, you'll see that it's actually closely related to the entropy, the change in entropy of ideal gas when you add one more particle. In this case, we're adding two particles, an electron on the N-type side and a hole on the P-type side. So it comes out of statistical mechanics, but I don't want to go into the details. It's outside of our course. But now that we have this expression, we can do an example problem and calculate what the built-in voltage should be. All right, we can do an example. let's figure out what the built-in voltage should be for a silicon diode at room temperature, 300 Kelvin. Okay? Then we know some things. We know that the band gap in silicon is approximately 1.1 electron volts. And now we have an expression for T times delta S. Okay? So this should be T times Boltzmann's constant times, and we have the expression right here, the natural log of these densities. Now the effective number of states in the conduction band is a number that you can look up for silicon. It's about 1 times 10 to the 24th electrons per meter cubed. Oops, excuse me. Whereas the density in the states in the valence band is about 3 times 10 to the 24. Let's suppose that our material has an actual density of electrons of 1 times 10 to the 20, both of electrons on the N side and holes on the P side. And this would correspond to moderately doped silicon. Not particularly heavy, not particularly light, lightly doped. So again, these numbers, they just correspond to the numbers I described in the formula above. Furthermore, the temperature is 300 Kelvin. Boltzmann's constant, I'm going to write down here in units of electron volts per degree Kelvin, and it's 8.67 times 10 to the minus 5 electron volts per degree Kelvin. Okay? And then we have this term, natural log of, well, you can see it's, if you evaluate this, it's 3 times 10 to the 8th. Okay? Very good. And now we just use a calculator to figure out the answer. So 300 times 8.67 times 10 to the minus 5 is the following. It's 0.026 electron volts. That's KT at room temperature, a useful number to sort of have in the back of your head. And the natural log of 3 times 10 to the 8th, well, 3 times 10 to the 8th is a very big number, but we're going to take its logarithm, and that'll be much smaller. And 3 times 10 to the 8th natural log works out to be 19.5. And so the product of these is 0.51 electron volts. Okay? So what we're saying is that when an electron goes around the circuit to the other side of the junction, so that in aggregate we end up introducing a hole on the P side and an electron on the N side, that 0.51 electron volts of thermal energy will leak into the device from the outside environment because we've increased the entropy. Okay? And that means that the built-in voltage, let me do this, let me write it like this. This means that the work that must be done per electron, which is Eg minus T delta S, will just be 1.1 electron volts minus 0.51 electron volts, which is approximately 0.6 electron volts, which, in fact, is about what we saw in our demonstration. Okay? All right. Or that is, to be clear, at 300 degrees, the built-in voltage, which is delta mu over E, works out to be about 0.6 volts. Whew. I know it's kind of complicated, but this effect due to finite temperature, it turns out to be important, particularly when we talk about devices like solar cells. And I wanted to show you where it comes from. Okay, let's stop here.